Okay, so let us begin. So last time we introduced the topic of antiderivatives, which is when we try to reverse a derivative. And so we saw that an antiderivative is a function, antiderivative of f of x is a function in f of x such that take the derivative of that guy, you get f of x. We also saw there was a notation for this. To say that this guy, f of x dx, represents the antiderivative plus some constant, because if you differentiate a constant, you will get 0. So that wouldn't have shown up. So we looked at some of that. We also spoke about some important remarks. One, we can get antiderivative rules by reversing derivative rules. Two, antiderivatives are useful. We're going to see other ways in which they're useful. And we also saw that antiderivative is also known as integral. And this guy, we can talk about it as the antiderivative of f of x, but a lot of people just say the integral of f of x, because integration is the process by which we will compute antiderivatives. And more specifically, I didn't mention this last time, and when I mention the other kind of integral we'll be looking at, you'll see why they have distinctions. So this guy will be called, it's the integral of f of x. But specifically, it's called the indefinite integral of f. And it's called indefinite because we don't really know for sure exactly what it is, because there's just a plus c here, and we might be given information where we can determine what that c value is, as in the word problem that we did, but we might not always know what that c is. So it's not super definite which antiderivative we're talking about. The antiderivative is not unique for a function. Every function can have either no antiderivative, or it can have an infinite number of antiderivatives. So it's not really sure which one we're talking about unless we're given extra information. So that's kind of where we wrapped up last class. Here's the third remark, and this is where we're going to start segueing into the next phase, which will be continuing Calc 2, but we're going to get things started off here. It turns out that antiderivatives have an interesting connection with area of all things. Now that might seem probably a little strange, but let's look at something, and then I'll give you a specific example where you can see this being applied, and then we're going to talk about the theory behind it. So suppose f of x is a function, and it's defined and considered on the interval a x. So this is just an interval. I fixed the starting point. It's a definite constant, but I let the endpoint vary. I can stretch this interval or contract it at will, and this is a variable right endpoint. So I have a function and I'm looking at it on some interval. You know, so like, so it's doing what it wants to do. That's my f of x. Let's say I start at a point A, and I'm considering the interval all the way up to some other point that it's x. Okay? So I'm thinking of the function on this interval. But this thing can be stretched and compressed at will. We're assuming that, maybe you can assume that it's continuous. That'll make things a lot easier. In fact, we're going to need that for some of the theorems we're going to be proving. So it's pretty much continuous everywhere we want to look. So I could extend this at will. I might even extend it even a little further, say to f of x plus h. But I can move it at will. And so now I want you to also suppose we could find a function. Now, I'm not saying that we can. I'm not telling you how to do it, but I'm going to say pretend that we could. Big A of x, that gives the area under f on x. Okay? So let's pretend we can actually find a function that's going to give us the area here. So if I want to know what's the area here, I'll simply plug it into the function a of x. Tell me what your endpoint is, and I'll plug that number into this function, and it's going to actually tell me what the area is at any point, right? So this could be 1 and x is 2. Oh, plug in 2 into this function, it'll tell you the area between 1 and 2. Plug in 3, it'll tell you the area between 1 and 3, etc. So suppose that we could find such a function. Let's examine some of the properties that this function would have to have. I would like to examine one particular property specifically. And I'm going to reveal this property by doing a little exercise on this example. Okay. So suppose I construct a rectangle here. That it touches the left side and then cuts off. And on top of that, I create another rectangle that touches the right side and cuts off. So I'm considering that little piece on it. Okay. So there are a couple things here. So let's start tweaking this a little bit. Okay. So think of this guy. This is another rectangle, which I'm going to call R. Clearly we know that its base length is going to be h. And I'm going to randomly call its height n, just for what it is. And now I want you to consider this expression. So this is, I want the area under the function up to the point x plus h. Right? So this guy gives us the area up to x. So between here and here. Let's say I want to actually find the area all the way up to here. And so that would be a of x plus h. And so that would include this area here. In addition to that, so I'm looking about for the area under f from x plus h all the way back to a. and then look for the area here all the way back to there. So I'm subtracting two areas, so notice that I will be taking this entire area minus that entire area, and I would only get the blue area. So I want you to notice that this will actually give us the blue area. I didn't know that. Find the area all the way up to x plus h, find the area to x, and subtract the second one from the first. You'll be left over with that blue area. Now here's something I want you to notice about the blue area. How would we actually compute the blue area? Well, there are a couple things I want you to notice. So, first of all, the blue area will consist of the part of the smaller rectangle So this is the area of a small r. Plus, you'll notice that we'll also have a little bit of area left over here, right? And because I don't want to worry about naming this, let's just call this some excess area that this rectangle missed. Now let's actually look at what these guys would be. Area of the small r, well, the small r is just a rectangle, so it's going to be length times height. The height, though, is actually given by the function f of x. So this is f of x times h, plus this little excess, which we don't know enough to actually figure out a formula for that, actually. However, one thing you can note here is that if you look at the area of the big R over H, now the area of the big R is going to be n times H. So this will be n times H over H. Notice that this will cancel and you'll just get n, okay? And what I want you to notice further is that the smaller I make this window, the smaller the H is that area is going to get, right? Which means, consequently, the smaller part of that area will also go to 0. And so in other words, n is going to approach 0 as h approaches 0, and consequently, the excess portion over h will approach 0 as h approaches 0. So that's kind of the setup. These are some things we can notice from the setup. And okay, why is that interesting? Well, let's see why this is interesting. So since now I can write a of x plus h minus a of x is equal to f of x times h plus the excess, I can divide both sides by h. It's going to be some positive number. And now what I'm going to do, this looks quite familiar. It's a difference quotient. And so we like taking limits of difference quotients, so I'm going to do that. Now we see something interesting. It turns out the limit of this expression, the difference quotient for the area function, well, that's just a derivative by definition. Limit as h approaches 0 of f of x is just f of x, is there no h's in it? And we see that the excess over h portion will go to 0 as the h goes to 0. So this guy's going to go to 0, and we're just going to be left with that. Now what you notice is the area function will have this property. If I take its derivative, I get the original function under which I was trying to find the area in the first place. Very strange. So in other words, in this case, the a of x function is an antiderivative of f on this interval. Which is kind of strange. Why would anyone even think to even try something like that? Well, the first thought probably came from one of the original examples that we considered when we were developing the derivative. We wanted to figure out a way to find out how fast something was moving. So we dealt with a very simple case, something moving at constant rate, and this was our way earlier example. Okay, we had this object where we're measuring its distance in miles versus time in hours. And I believe the numbers were 3 and 150. And we pretended it was at constant speed, and we saw that the slope gave us the velocity of this object. Right? And that led us to derivatives. Now, what you want to notice here is that if someone were to do something like this, and to chart over the same time period the actual velocity, you start to notice something curious. Well, we saw that the slope of this was, 150 over 3, so it was 50, right? So here it was 50 miles per hour. And it's constant speed. So if I were to graph the velocity function, this will just be a constant function at 50, right? Running over the period of 3. Now if you look at the area under that function, what is the area? It turns out to be 150, which happens to be the distance we covered over that time. Right? And this would be something that's always been noticed. Like if you start tracking distance and you start tracking speed for the same object, you realize that the two graphs have a very curious connection. The area under the speed graph is always going to be the slope of the distance graph. You'll notice that this was equal to S evaluated at 3 minus S evaluated at 0. And this would always seem to be a connection. And furthermore, derivatives taught us the lesson that S prime of t was v of t. In other words, S is the antiderivative of v. And basically what this suggested the very important fact, right? This is the fact that caused us to run down that rabbit hole that we're about to run down, is this suggested that the area under the f of x on some interval a, b seem to be its antiderivative, the difference between its antiderivative at the endpoints of a, b. Seem very curious. Right, and this is again where big F is the antiderivative of small f. Now, of course, you can see that in a couple examples. You can kind of see it in the little thought experiment we did earlier. But to be able to say this in general, a math person is not going to be convinced with seeing a few examples. He's going to ask, is this true in general? That's very weird. Maybe it's just with this particular example. Could something like this possibly be true in general? And so that would be the next question they'd ask. Turns out the answer is yes. And this leads us to integral calculus. Right? So pretty much, first considering the slope of a graph, figuring out that we could talk about speed in terms of slope, led us to integral calculus. Now we realize a curious connection between, if I then think of speed itself as a function, there is a very intimate connection between these two situations. And it turns out area was that connection. And so that's the thought that kind of started to bridge these two schools of thought. So remember, way back in the beginning of the class, I told you, okay, there were two fundamental problems that calculus was meant to solve. The rate problem and the area problem. And we knew a lot about solving each of these problems individually for a long time. No one even knew that they were connected. But then someone noticed this. So we have all this math over here that's worrying about how fast things are moving. And we have all this math over here worrying about what's the area of stuff and how much space things take up. And then someone realized, well, look at them as functions. Which is, I know to us it seems like a very simple thing at the time. But then you remember something like the XY axis that we're so fond of drawing, that we've been drawing ever since we were a little kid. This was invented around the 1600s, so mankind couldn't even visualize equations the way we do for a really long time. So it took a really long time for us to actually start to making these connections. Once we could start looking at the pictures of an equation as opposed to just the equations themselves, a lot of things started jumping out at us that didn't before. And it turns out that we were studying two sets of problems that seem to be totally disconnected, have nothing to do with each other. But it turns out they did have to do with each other. We're now going to attack the area problem. And we're then going to look at specifically how the area problem is connected to the rate problem. This connection is called the fundamental theorem of calculus. So remember, this is the problem. How much space does something take up? And like the rate problem, it's a very vague statement. But of course, everyone would be able to point to an example that they care about of why they would care about how much space something takes up. So I gave the example of some guy who owns land that is very irregularly shaped and he's concerned about his property taxes. He wants to know, are you really taxing me the right amount? How much space does my land actually take up? Okay? So something is quite vague, and so this was a very difficult problem to solve. But it turns out that these are problems that we actually solved pretty early on. I mean, Archimedes solved this problem 300 BC, something like that. So we've actually known how to deal with this for like a couple millennia. But nothing was ever packaged into a nice little theory. You just had little guys doing their little thing, and everything was very computationally intensive. Every problem was a different problem, you know? We had certain methods that we thought of, oh, we know that this method would work, and so every time we'd apply it to a different problem, yes, we're thinking of the same method, but it wasn't formulaic. It was just based on this example, following our method, it would have to look like this, and then we kind of went intensely through the computational aspects of it. It wasn't until 1600s Descartes invented the XY, the Cartesian axes. And then we started picturing functions. And then people started noticing these things about graphs. And then Newton came along and said, hey, these two things are connected. And that is what created calculus. Well, technically speaking, it probably started with Newton's math teacher, actually. And Newton kind of packaged some of his initial thoughts. But yeah, how much space does something take up is the problem. And so here's the solution that they came up with. And it's going to be very rudimentary. Like I told you, we've known about this for a long time. So basically, the solution was dissect it. Dissect the object into a bunch of small pieces that you do know how to find how much space they take up. So that was the first thing. So we're going to have some object. It's going to be weird. It has a weird shape. How much space does that take up on the board that I just drew? Oh, well, I'm not sure right away. It's not a very nice shape. However, we have a convention for talking about the area of rectangles. So what I would probably do is I would just dissect this thing. Into a bunch of rectangles. And then what you do is add up the areas of all these pieces. And that was it. That was the area problem. That was their strategy. So as you can see, it was very computationally intensive. Every new shape they saw, they really had to start all over from the beginning. There was nothing theoretical that they could just compute without even noticing the intricacies of the shape, okay? And so, of course, the idea of here is the more dissections you make, the better your approximation of that area would be. So what they would do is they would add up the areas of all these rectangles, and then when they got to the edges where something was just a part of a rectangle, they just approximated, okay, that's about a quarter of the rectangle, or this is about a half of the rectangle. And so they'll add up a bunch of whole numbers, and then they add up a bunch of fractions. It's very computationally intensive. And then they would, well, sometimes they wouldn't do it like that, right? They get the biggest shape that they could possibly fit inside, find that area, and then they do this process on the edges. So something like that would be a smarter way to go about it. But this is basically the solution to the area problem. Cut it up into a bunch of little sections that you know how to find the area of, add up all these areas. And so this was very computationally intensive. It worked, and you can make it work even better by using more rectangles, but it's very tedious, not very nice, not very formulaic. And so we sought a better way to do things, and it started out by us searching for, is there a nice way to add up a bunch of things very efficiently? So that's where the area problem started. Okay, this is how we're going to find area. Oh, it turns out that this is super annoying to do. Is there a nice way to add up a bunch of things? So the question came, is there a nice way to add stuff? Now remember, at this point, we didn't know about a connection between antiderivatives and rates of change and derivatives, or anything like that, right? We're starting with the error problem. We're figuring out how much space this thing takes up. It's very tedious, and so we wanted to find a nice way to add stuff. And this came along much later, but ultimately, this ultimately led to what we call sigma notation. Now, sigma notation is in the appendix. I believe it is E in your textbook. So we pretty much wanted a formulaic way to start adding stuff up. And of course, if we're going to write a formula, we'll need new notation, and then we'll look at what we want this thing to be able to do and how it will be able to do it. Now, sigma is just, it's actually a Greek letter, and we usually use it uppercase sigma. Right? So it's kind of like the equivalent of the Greek S for sum. We're summing things up. And so that's what we called it. Because the Greeks had a lot to do with it, obviously. This thing was around the time and region of Archimedes. So the Greeks were naming everything. But this is going to segue into sigma notation. So let's see what I want to tell you about that. And it turns out we're going to start building up our theory of finding areas. And it's going to come around full circle and connect to derivatives, which very few people saw coming. So let's say we have a list of numbers that we want to add up. The numbers could represent areas of rectangles, they could represent anything else. We really wanted a theoretical foundation of adding stuff. So once they decide we want a good way to add stuff, yes, they were cared about areas, but let's do it in general. Let's come up with a theory. Suppose we have a list of numbers. Such a list is called a sequence, right? So when you get to Calc 2, you'll talk about that. So we'll cover a topic called sequences in series. And so you can have a list of things that you put in some order for whatever reason, and you call that list a sequence. We define the summation of these numbers via. So here's the notation. You have this sigma thing. And since you're calling numbers by some variable where the subscript is just representing the place it comes in the list, we call it a little I. And we can say where I is going from. I starts at 1 and it goes all the way up to n. This is using the sigma notation. And basically this is shorthand for A1 plus A2 plus A3 plus AN. So anytime we want to theoretically have a shorthand for saying I'm adding up a bunch of things, we can use this notation. So this is what it means as a definition, that's the notation. And this over here, because it uses the word sigma, this is called sigma notation. And in general, this entire thing, either side of the equation, we would call it a series. So a sequence is just a list of things in some definite order. A series is the sum of the things in that list. So this is called a series, aka sum, aka summation. But most people are going to say series. Most math people would say series. But is a finite series. But they can be infinite. Now that might be a little word thought, but let's just define it. So if we're talking about an infinite series, this means basically we're summing an infinite list of things. So we have the summation of a bunch of things that I'm going to represent by AI. My I starts at 1 and it never stops. It goes off to infinity. And then this is just A1 plus A2 plus ... It will keep going. Now at first you might wonder, does that even make any sense? Can you add up an infinite number of things? Won't you always get infinity if you're adding up? If these numbers aren't all 0, won't you always get infinity or negative infinity? Does it even make sense to define such a thing? It turns out it makes a lot of sense to define such a thing, and the answer is no, you don't always get infinity or negative infinity. And there are some times where you don't even get a number at all. Infinity is kind of weird to deal with. But it was very important for the theory to be able to talk about summing an infinite number of things, and we'll talk about that pretty soon. So I wanted to introduce that notation, which I did. Let's do a simple example. We will then, so when it comes to these guys, there are some properties that you should know and some formulas that you need to know. There are 4 important formulas. I'll probably derive one of them. But before, let's just do a simple example. Oh, by the way, AI can be thought of as a function whose outputs are the members of a series sequence. Its inputs are the natural numbers. Okay, so that means 1, 2, 3. So we're doing something to count the place, the position that you're in. Some people start from 0, but the same ideas would hold. Let's do a simple example. Let's do AI equals, say, I plus 2. Right? So you can imagine what this is listing. So this means I have a bunch of things in this list that go the following. A1 would be 3, because I would just put 1 plus 2. A2 would be, I would plug in 2 here, 4. A3 would be 5, etc. And so this is pretty much a list that starts at 3, 4, 5, keeps going up. Okay. And so AI seeing this is me representing that list, just counting from 3 onwards. Okay. And so now I can ask you something like the following. And this is just to get you used to the notation. It's not supposed to be insightful or anything. So I can say what is the sum of this AI? I go from 1 up to 3. And so that would just be, well, I plug in 1, plus plug in 2, plus plug in 3. 3 tells you where you stop, right? This tells you where you start. So this says start here, and you would end here. And you could actually make the start and end pretty much anything you want, any positions in the list. But this would be, of course, A1 is when you plug in 1 here, that's 3, plus A2 is when you plug in 2 here, that's 4, plus A3 is when you plug in 3 here, that's 5. So this will be 3 plus 4 plus 5, and that's what, 12? I could start somewhere else, by the way. And so I could say something like, let R start at 5, and I want it to end at 8. So this of AI, this just means I'm doing A5 plus A6 plus A7 plus A8. And that's going to be 5 plus 2, 6 plus 2, 7 plus 2, and 8 plus 2. And that's what I do. Right? So that's a notation. It's not anything special. And so far you might say, well, there doesn't seem to be anything special. We're just adding the way we've always done. Okay, but it turns out that the notation is going to make it very easy for us to determine certain properties and formulas. And once we can do shorthand with certain summations, we're actually going to apply series to solve problems. So you'll see how you can use them in all their glory. Right now, I don't think this is looking like anything special, and it's not. So still seems cumbersome. You just put a nice notation on the other side, but you didn't actually help us solve anything. It turns out we can derive helpful formulas. Now, here's one formula. I have a lot of time. Maybe I'll construct it for you. So, this comes from legend. There's a story about the famous mathematician Carl Friedrich Gauss. I don't know if it's true or not, but I wouldn't be surprised if it is, because he's kind of, a genius. And so, one day, when he and his friends, he was very small, maybe 4 or 5, they were at the age where they were just learning to add things with literally physical objects. They had to count them and add them and then talk about the total group. And so one day when they were kicking up a ruckus, their teacher got really upset and was like, everyone sit down and add all the numbers from 1 to 1,000 right now. And that was, she just thought she had them for the day, maybe even for the school year. But it turns out little Gauss had the answer in a few minutes, maybe 2 minutes. He came, oh, this is going to be the answer. He was like, how did you actually do that? How did you add the numbers from 1 to 1,000 so quickly? And so little Gauss had, little known to his teacher, since he's been at home, he's been doing arithmetic for a while now, at 4 years old. And so he started to notice patterns. So he realized that the goal was to add the numbers from 1 to 1,000. And so we can call that S. And he's like, okay, so teacher wants me to find S. That's how he started thinking about it. But he noticed something curious after looking at it for a few seconds. He's like, you know what? Addition, it doesn't matter what order. It turns out that 3 plus 5 is the same as 5 plus 3. So this would be the same as if I turn things around. And then he noticed something more curious, if you add these guys in line, you'll notice that you always get the same number. So he started adding these up. And he's like, well, if I add the first one, I'll get 1,001. If I add these, I again get 1,001. And I add those, I get 1,001. All the way down to here, I get 1,001 and 1,001. And of course, there are 1,000 numbers here. So there are 1,000s of these thousands and ones. But what he did was he added the list, so he actually get twice what he should have gotten. And so then he realized that, oh, 2s is just going to be 1,001 times 1,000, and then divided by 2. So while his classmates were there counting on their fingers, trying to figure out this very difficult problem, he was just multiplying 500 by 1,001. And for little Gauss, it didn't take too long. But it turns out you can do this in general up to n. I can talk about the sigma of the formula I, where I is going from 1 up to n, and that's just me adding the first n positive integers, right? And again, I could do this twice, put n plus n minus 1 all the way down. You'll realize that they all add up to n plus 1. You'll have n such things adding up to n plus 1, and then you would divide it by 2. And it turns out that you can then come up with a formula for this guy. It's n times n plus 1 all over 2. And that's one of the first helpful formulas. You're going to see why sigma notation is going to be very useful. Because we can derive a few things, and then we can get a nice formula in terms of sigma notation, then we can use those formulas to do other things with them. And it builds on itself. It gets really sophisticated and really efficient really fast. And this is one of the 4 formulas that you'll need to know for sigma notation, and we'll deal with the others later. But this is the beginning of us solving the error problem. We need to know how to add efficiently, and sigma notation provides an efficient way to do this. And we will continue this journey next week.